Okay, so welcome back for a new experiment today, that is on Norton's theorem. It is very similar to the previous experiment that we did, that was Thevenin's theorem. But only thing over here, instead of calculating the equivalent voltage, we'll have a current source. Okay, so let's see what this experiment is all about. So aim here is to verify the Norton's theorem for a given network containing the DC source. DC is for direct current, and resistors. Of course, the apparatus is very much same as that you used during the uh, Thevenin's verification of Thevenin's theorem experiment. Uh, Only thing, like instead of voltage source, we will have a current source over here in this case. Fine. Next, the theorem. Theorem also reads very similar to that of the Thevenin's theorem, but there are small changes. Let me just read it for you. For example, any linear bilateral network containing one or more sources connected to terminals A and B of a load can be replaced by a current source. Okay, by a current source. In case of Thevenin, it was voltage source, VTH, right? It was VTH. In case of Thevenin's, here we have current source IN, the subscript N for Norton. Okay, in parallel, in case of Thevenin's theorem, it was series, correct? In case of Thevenin's theorem, it was series. Here we have in parallel. So remember two things. One, instead of voltage source, we have the current source in case of Norton's theorem, and this current source is in parallel, unlike the voltage source which was in series in case of Thevenin's theorem. Fine. Now, with a resistance Rn, which is equivalent resistance, same as that we had got in Thevenin's theorem, okay? But just that since we are in Norton's theorem, we will put a subscript N to it instead of TH. IN is the current across the terminal, okay? That is the Norton terminal AB when the load is short circuited, okay? In case of Norton's theorem, you will have to short circuit the load. Fine. In case of Thevenin's, it was open. Over here we'll have to short circuit it, right? And Rn is the equivalent resistance across the terminal with low A and B removed and all the sources replaced by their internal resistances. Is that fine? Okay, so this is the theorem, very similar like Thevenin's theorem, but look at what are the changes. One is the voltage source is replaced by current source. Instead of series, we have parallel in this case, right? And then we have the terminals short circuited in this case. Fine. So let us quickly look at the circuit diagram, which is very similar to the Thevenin's theorem. We have taken the same circuit that we used in Thevenin's theorem. We are taking for Norton's theorem. Okay, same resistors of value 100, 100, 100 and 150. Okay, and same circuit board we are taking, and this is the same circuit diagram to start with. Okay, for the Norton's theorem also we have this voltage source, the battery, small battery, whose voltage we'll find using the multimeter. Okay, we will use multimeter to find what is the voltage. It will vary every time. Next time, in case you come to perform this experiment in the lab, then this voltage will be a different one, little bit up and down. Okay, but in and around 1.4 to 1.5 or little bit above 1.5. okay, sometimes. All right, so this is the circuit, same circuit that we have given. We have the milliammeter connected here. I've told you last time in my class that you need to put the polarities. Okay, so I put it in this one, and similarly you need to repeat it even for Thevenin's circuit. Fine. So this is the circuit. Now what does Norton's theorem says is that if I replace this, I can replace this in such a way that I can have an equivalent current parallel to the Norton resistance, equivalent resistance. The entire circuit can be replaced with Rn, okay, and given a current IN, so that the current, whatever we observed here, okay, in this case is same observed in this case too. Just like Thevenin's theorem, is only thing, instead of IN we had VTH, voltage source, okay, and we found that the current that was observed in the given circuit and the equivalent circuit were same, right? Over here also we will have to observe similar observations to show that Norton's theorem is correct. Okay, fine. So let's take the same circuit as I told you, okay, and this is the equivalent resistance that we need to calculate. We have calculated it last time. Of course, you need to remove this load resistance for doing that. Okay, for doing that, just remove this load resistance for calculating the RTH. No, in this case, it is not RTH, it is RN. Okay, equivalent resistance is RN. I will not calculate all over again. You have already done it in Thevenin's theorem. Just same to same circuit it is. Do it again, and it came to 75 ohms. So here also it will be 75 ohms. Okay, so remember you need to remove this load resistance. Okay, and calculate these equivalent resistance in case of Norton's. Okay, now what about Norton's current IN? What do we do in case of Norton's current IN? Fine, so we have this RN equal to 75 ohms. Now we need to calculate what is IN. What is IN? We need to calculate. So for that what we do is we short circuit this circuit. Okay, we can short circuit this. Okay, now when you short circuit this, what happens? It is as good as no current will flow through this resistance, because your short circuit is as good as this is not there. Okay, so what happens is that your equivalent circuit will be now having these resistances. Correct. Okay, we'll have these resistances, and of course we'll have this voltage battery. Okay, and it will be like this, right? So we'll have R1, we'll have R2, and we'll have R3. Okay, and we'll have R2. Fine. Okay, now we need to find out the equivalent or the Norton current that is flowing in this circuit, because this circuit we have short circuited, so this is as good as this particular resistance of 150 is not there. So we need to calculate what is IN in this. So there are many ways to do it. Let me just give you the simple one for this simple circuit here. First of all, we need to measure what is the voltage using multimeter, and for this experiment when I was doing, it has come out to be 1.422 volts. Okay, now V is equal to IR, right? Okay, so therefore I is equal to V upon R. Okay, so now if I take this 100 and 100 ohms, it is like they are parallel to each other. Okay, so 100 and 100 parallel will be 2 upon 100, that is 1 upon 50, right? So therefore this particular resistance will be 50, right? And now that 50 is in series with R3, okay, which is also 100. So 100 plus 50 in series is 150. Okay, is 150. So the total current flowing here is 1.422 voltage, that is measured using multimeter, divided by the resistance 150. Okay, that is coming out to 0.00948 amperes. Okay, amperes. Now we know that this current will be split into two equal half, because the current will flow here and current will flow here also. Okay, it will two equal half. So we can simply divide this by 2, and if you simply divide this by 2, you will get the Norton's current as 0.00474 amperes. Okay, 474 amperes. So that is equivalent to 4.74 milliamperes. That is equivalent to 4.74 milliamperes. So we have got IN also, that is 4.74 milliamperes. Okay, so we have the equivalent current, we have the equivalent resistance 75 ohms. So now we need to perform experiment using this given circuit first, calculate our load current IL, and again replace the entire circuit with a current source of 4.74 milliamps in parallel to the equivalent resistance 75 ohms. Okay, equivalent resistance 75 ohms, and you should get IL again. Okay, and if experiment is good, then both the ILs should be very similar. Okay, both the ILs should be very similar. Okay, so what we'll do now is, without wasting much time, go to the laboratory, perform this experiment, note down our readings, and come back again for calculations and see the graphs, and let's check whether the Norton's theory is verified or not. Fine, so see you after the experiment. Okay students, so we are ready for performing our experiments, and as you can see, it's the same circuit that we had used for Thevenin. We have 150 ohms over here, and these three resistances are 100 ohms each. Brown, black, brown, brown, black, brown, brown, black, brown, and this is the brown, green, brown. resistance. Fine. So we have done the calculation for equivalent resistance and also the Norton current already in the first part. So we will perform this in the second part. We are replacing this circuit. So let's first take this circuit and calculate how much, what readings are we going to get in this. Okay, so for that what we do is first we have the circuit. Let's connect the positive. Let's connect the positive to the positive and negative, that is black to black. Okay, so this way this part is ready. Then we have the milliammeter which is connected this end. Milliammeter goes to the load resistance, right? So I would suggest that initially just remove it, even though we are going to take the 0 ohm resistance, just remove the infinity key and connect this to the resistance box. Fine. After that, connect this end to this wire here. So we have this wire, black one. Okay, and with this our circuit gets completed, right? Okay, so since this is infinite resistance, there is no current shown, so the moment I put that, then you can see some current is already recorded in the milliammeter from the circuit. Okay, battery we have already found using the multimeter. It is around 1.422 volts. Okay, so this is the reading that we have got. Let us record the reading as 2.8 milliamps. Let's take off 10 ohms, and the reading is it's between 2.6 and 2.8, so let us note it down as 2.7. Let's take out 20 ohms, and it is 2.6. Next we have is 30 ohms, so we have 2.4. Let's take out 50 ohms from the resistance box. This is your circuit. Okay, let's take out 50 ohms, and it is 1.8 and 2, so 1.9 we can write. Let's take out 60, 1.8. Let's see for 70, that's 1.6. For 80, it's 1.5. And so let's take out 90. It's 1.4, and let's take out 100 ohms. It's 1.4. Fine. So with this we have finished the first part of the experiment, and in the second part we are going to replace the circuit, okay, and connect the resistance 75 ohms which we have already calculated, and the Norton's current, okay, which we have calculated it to be 4.74 milliamperes. Fine, so we will connect it parallel to the circuit. So see you in the second part. Okay students, so I'm ready for the second part, part 2, in which we have this current source, and we need to adjust. As we calculated, it is around 4.74. We will try to adjust it very near to 4.74. Okay, so this is 4.75. That's good enough. Okay, that's good enough. So let's use 4.75, or whichever is the closest one that we could get to. Okay, 4.74, that's great. So we have got 4.74, 4.75. So I'll just remove this multimeter now. Okay, so our current source is ready. Let's switch it off. Alright, and let's keep it connected, the current source, so that we can use it. Okay, so what I would suggest you in doing this experiment is first connect this part. Okay, this is you have calculated the equivalent resistance to be 75 ohms. So I've already taken out 75 ohms from the resistance box. We have this milliamp meter. Let's connect it here. Okay, so we have the resistance box which is going parallel to the milliamp meter, and this is the other resistance box, that is your load resistance. Okay, so initially to start with, you can even take out some infinity key and keep it out just to start with. Alright, and just let this go parallel to the resistance box, which is equivalent resistance box, 75 ohms. Fine. Okay, so I would suggest that you do this first. Alright, and once done, this is done, then you connect this power source, that is current source that is given to you, and parallel to this. Okay, so that should help you. Fine. So let me just do that. So now we are connecting this power source, current source I mean, and parallel over here. So once done, we have the milliamp meter. We can switch this on. Of course, infinity key is off, so you will not see any current. So let's put this infinity key, and there you see some current. So fine. So once we have done this, you can see we have got some current, and it is around 2 point, or not 2 point, it's around 3.2, which is a bit higher than what we had got initially. We had got 2.8, we have got 3.2, no problem. So this is for zero resistance. Let's take out 10 ohms. So as we take out 10 ohms, it is around 2.8 and 3 in between, so 2.9. Let's go for 20 ohms. It's around 2.6. Next, go for 30 ohms. That's around 2.4. Let's go for 40 ohms. It's between 2.2 and 2, so 2.1 I can note it down as. Let's go to 50 ohms. That's around 2. Now let's go to 60 ohms. Let's put back these extra resistance. So that's 60 ohms. So 0, 10, 20, 30, 40, 50 is done. So 60 ohms. And it's around 1.8. Let's go to 70. That's between 1.8 and 1.6, so 1.7. Let's go to 80. That's around 1.8 now. Sorry, 1.6 it is, 1.6. And then 90. That's still on 1.6. And lastly, the 100 ohms. That's 1.5. Fine, so with this we have finished even the second part. So as I've told you, what I would suggest is you connect this circuit first in, okay, and then you connect this current source parallel to this one. Okay, so that way you will get the readings properly. Fine, so let us now go back and do the calculations for Norton's equivalent circuit and Norton's given circuit, and let's see whether Norton's theorem is verified or not. So see you for the calculations. Okay, so welcome back. We just perform the experiment. We have seen that the readings are quite good. Not like Thevenin's theorem, we didn't get exactly equal, but good enough to say that they were same, that were similar. Okay, so here we have the reading from the given circuit, we have the reading from the equivalent circuit. Okay, so from given circuit we got 2.8 and equivalent circuit we were getting 3.1. Similarly, we could see that the readings are not exactly same, but they are in and around similar readings that we were getting using the equivalent and the given circuit. Fine, so in the both were almost same. The theoretical calculation is done using this formula. Okay, V is equal to IR. So obviously I is equal to V upon R. So IL, load current, is equal to V. This will be like Vn, right? V is equal to IR, the Norton current, into the equivalent resistance upon the R, the total R, that is the equivalent resistance, plus the load resistance that is changing here, right, from 0 up to 100. Okay, so you can do this calculation to get the theoretical reading, and you see the theoretical reading is bit on a higher side compared to what we got experimentally. Okay, what we got experimentally. So we need to now plot the graphs of these two experiment and of these two data that we have got, and see how much it is in agreement with the calculated values. Fine, so let's plot the graph. So when I plot the graph of a given circuit, remember the graph that you need to plot in case of Norton's theorem is inverse of the current versus the load resistance. Okay, so this is the thing, and of course you don't have to write all this, you have to write your scale. Okay, as you write in your school, the scale 1 unit is equal to what it is. So when you're plotting the graph, you see, so this is the intercept. You can ignore the errors, this is coming computer generated, so you don't have to worry about the errors. Okay, so you will get a graph like this, intercept, so you will have to extend this down. Okay, so it will, according to this data, it should intercept at 0.32, so you can do that. Okay, 0.32 means somewhere here it will be. Okay, it will intercept somewhere here. Okay, the intercept will be at 0.32 and slope is 0.0041. Now remember, this is Norton's theorem, so do not go by intercept as the Norton's equivalent resistance. Okay, that is not the thing. The thing is here, the Norton current is inverse of the intercept that we have got. Whatever intercept you get, inverse it. Okay, invert it, and whatever answer you get, that is the Norton current, 3.125 milliamperes. Okay, and the resistance, Norton's equivalent resistance, is the intercept, y-intercept upon the slope of the graph. So y-intercept is this 0.320 upon the slope, that is as per the generated thing. You may get little different when you're using your graph paper. It is 0.0041, and the resistance from the given circuit has come out to be 78 ohms. Okay, we had got 75 ohms, here it is 78 ohms. Moving on to the equivalent circuit, the answers are much more different. Again, replace this by slope. Okay, and again you'll have an intercept. Ignore the errors, you don't have to calculate errors, you just calculate intercept and slope using the graph. So the Norton current is the inverse of this, that is 3.165 milliamperes, and resistance, equivalent resistance, has come out to be 85 instead of 75, almost 10 ohms more for an equivalent circuit. Fine. So if I just compare the results that we have got from calculation, we got 75 ohms, and the Norton current was 4.74 milliamperes. From the given circuit, it was 78, very close to 75, and current little lower side, 3.125. Equivalent circuit, the resistance has come little higher, but the current almost remains the same. Okay, so I would say it is good enough, not so bad. Okay, good enough, not so bad. Maybe there were some fluctuations or something like that from the current source that we took. Okay, otherwise the answers are not so bad, it is quite good. Okay, within the limits of the error, so nothing to worry, not so vague answer, quite good answer. So in the result, you can simply write that the currents in the given circuit and the equivalent circuits are nearly the same and are within the experimental errors. Okay, experimental limits of the errors, and hence the Norton's theorem is verified. Okay, so with this, so you can see that we have actually verified a Norton's theorem. Okay, with this, so Norton's theorem actually shows that the given circuit and the equivalent circuit would be the same. Okay, so aim of performing Norton's and the Thevenin's experiment or using that theorem is to just simplify the complicated circuit. Okay, and we have two theorems now. We have many more, but these are the two theorems which we have taken for practical purpose. Okay, so so with this we have finished Norton's theorem. I hope you have enjoyed the experiment. Okay, and see you next time for some different kind of an experiment. Okay, so till then, thank you.